Our last example is about Quicksort. We have studied Quicksort in our fundamental course, right? Do you still remember its time complexities? It has the best average case complexity, n log n, right? But in the worst case, still it runs in n squared time. So we call that version of Quicksort the deterministic Quicksort. It has the big theta of n squared worst case running time and big theta of n log n average case running time. And we have tried to prove that conclusion in the fundamental course, right? In order to obtain this result, we have to assume that every input permutation is equally likely. So how can we get randomization involved here? Think about this. What is the key to the runtime of Quicksort? The pivot, right? And we have learned about how to analyze a divide and conquer algorithm. If we want to obtain a result like n log n, we must make sure that every time the problem is divided into subproblems of smaller sizes. And it's not like from n to n minus 1, not a linear decrease. That will be the worst case, right? It has to be decreased by a factor like 1/2 of n, 1/4 of n, and so on and so forth, right? So one idea of randomization is this. How about choosing the pivot uniformly at random in hope that we can always split the set in the way we want? Here we define a good pivot as a central splitter. That is the pivot that divides the set so that each side contains at least 1/4 of n. If we can always find the pivot that is a central splitter, we should be able to obtain that n log n complexity. So here's the modified Quicksort. That is, we always select a central splitter before recursions. Always select a central splitter. Well, will it make things better? What if it takes too long to finally find a central splitter? Well, here we have the good news. We say that the expected number of iterations needed until we find the central splitter is at most 2. And the proof is simple. According to the definition, if we divide the set into 4 quarters, then these elements in between are all qualified to be the central splitter, right? So that means half of the elements can be central splitters. So that means we have 50% chance to hit a central splitter, right? And therefore, the probability of finding a central splitter in one hit is just 1/2, and that completes the proof. Then to find out the runtime of this randomized Quicksort, let's consider the types of the subproblems. We say that a subproblem S is of type J if the size of S, that means the number of elements in this set, is bounded below and above by these two functions. What does it mean? Here, 3/4 corresponds to the worst case. If the pivot we selected is either here or here, then we're going to have two subproblems. One contains 3/4 of n and the other one contains 1/4 of n, right? So 3/4 of n is the larger case. So in the worst case, if next time still we split it into 2 parts and the larger part contains 3/4 of 3/4 of n, that would be n times 3/4 squared, right? And so on and so forth. We just keep going like that, right? So each type J corresponds to the larger part of the partition. And we claim that there are at most that many subproblems of type J. Why? Well, since the total size is n, right? And each side is at least given by this function, right? So it's n over the smallest size. That gives the number of subproblems. So the expected time taken to solve all the type J problems is what? For each subproblem, it takes 2 steps to find a pivot, right? And it takes a linear scan to rearrange the elements around the pivot, right? So it takes linear time for each subproblem to rearrange the elements. So the expected time to solve all the type J problems is given by this. This is the linear scan time. That's big O of the upper bound of the sides times this is the total number of subproblems of type J, right? And they just canceled out somehow and leave us a final result of big O of n, some constant times n. All right? So this is the expected runtime for only the type J subproblems. And the number of different types is what? When we multiply n by 3/4, it's getting smaller, right? And smaller until we get 1. So how many different J's can we have? That corresponds to the number of multiplications, right? It's what? It's just log n with base 4/3. But that 4/3 doesn't matter, it's only a constant. So it can be written as big O of log n. So this is the expected runtime for one type. And this is the number of different types. Put them all together, we obtain that the total runtime will be n log n. Okay, so it's not bad, although it requires a uniform random number generator, and that is expensive. Alright, to summarize, the offline hiring algorithm is always correct, but it's less efficient, right? And the online hiring algorithm is efficient because we only hire once, right? But no longer guarantees the correctness. And we can only claim that we can obtain the correct answer with some probability. And this modified quicksort is always correct and is efficient. But let's keep in mind that this n log n is an expectation, not the real worst case time. Alright, and it's time to have your 6th research project about skip lists. And skip list is a data structure that supports both searching and insertion in log n expected time. So it's a randomized structure. And this project requires you to introduce the skip list and to implement insertion, deletion, and searching in skip list. And of course, do some analysis with different random numbers. All right? And so much for today.